Swayam Prabha. Digital India. Educated India.
Okay, students. So today I will teach you the level 3 detections for the biosensors. Let's use something advanced technique that can be useful for point of care diagnosis. So today one new technique that I will teach you is the level 3 detections. So before going to dip in the level 3 detection, I will teach you first a new technique, that is electrochemical impedance techniques, that will be very much useful for level 3 detections. Then I will show you different example for level 3 detections. So main concept of our today's teaching is the level 3 detections. Then I will show you how to optimize all the conditions for level 3 development. Then I will show you the design of the device for level 3 detections. So you can see here the main keywords for this talk is the level 3 and then point of care. So finally, if we can use this kind of technique for level 3, definitely it will be useful for point of care, because if we need level, then sometimes many steps can not be favorable for point of care diagnosis, because one step for just for antigen immobilization, then washing, then second step, right, then second step will be secondary antibody that conjugate with some level. So that can sometimes we need some extra steps that not be favorable for on-site diagnosis, because you need washing, maybe some expert person you need. That's why level 3 detection is very much useful for point of care diagnosis, because we don't need the extra steps. Then you may ask me, sir, why then we need the label? There is some utility, definitely, because with the label we can go for very high sensitive detections. Sometimes we may need very ultra low detection. That time we may need label. But sometimes, suppose your target analyte concentration is picogram or some nanogram level, or maybe more than microgram. In this case, you don't need very ultra sensitive detections limit. So in this case, you can go some detection technique where you don't need label. Let's come. So one important technique for this level 3 detection is the electrochemical impedance. So I will not go too much deep in this impedance technique. There is so many mathematical derivations. Thus, I will show you the tools and the useful items that's needed for level 3 detections. That's all for this EIS technique. Let's first try to understand what is the definitions of this EIS technique. EIS is basically the electrochemical impedance spectroscopy. It is definitely a electrochemical technique that helps to measure the impedance of your sensor surface. Suppose you have a sensor surface 1 and 2, right? So one surface not that much conductive, and one, and second surface, suppose you have another surface, it contains so many like different nanomaterial you use that are very highly conductive. So if you see like some electron mediation reaction, if electron transfer, if we measure in the one surface and the second surface, if we measure the electron transfer rate, definitely in the second surface the electron transfer rate will be much faster. So impedance is kind of it helps to measure the electron transfer kinetics, how fast electron is transferring through this electrode surface. So definitely the impedance of the two electrode will be much lower than one, right? So impedance value, right, impedance of 2 will be lower than impedance value of the 1, because it is highly conductive surface. So something like this. So generally impedance, you can see the equivalent circuit. So generally we draw a equivalent circuit for a sensor surface. Suppose like this is your sensor surface, and when you dip your sensor to a solution, definitely it is not in the dry conditions, right. So, we will have some solutions. So, generally we use potassium ferrocyanide and ferrocyanide reacts mixture. So, K3 FeCN6. So, here iron is the 3 oxidation state, and another reagent K4 FeCN6, here iron is the 2 oxidation state. So, this couple mixture we will use in 1:1 ratio. And here in the impedance spectroscopy, we will apply some potential. That potential will be the formal potential of this mediator, electron mediator. So, suppose if you measure your cyclic voltammetry of potassium ferrocyanide or ferricyanide, basically they are the one in the higher oxidation state, one in the lower oxidation state, and they are very much reversible reaction, right. So, it will be like this. So, before the impedance measurement, you have to collect a cyclic voltammetry of this electron mediator. Then you have to calculate the formal potential. So, formal potential basically, so it is you can see if you know this is the 0, here is the negative side, here is the positive side, up positive, down negative. So, if you measure the cyclic voltammogram for the potassium ferrocyanide, where iron is the oxidation state 2. So, it will oxidize, right. Then here we can stop. Then from here, so it is the oxidation, and the back side CV is the reduction. So, here iron 3 start reduced to Fe2, right, like this way we can stop here. So, this is your potential window for your ferroferricyanide mixture, right. See, so what is the formal potential? So, you have to calculate. So, this is your highest oxidation potential, right, where we are getting the peak potential. So, this is called peak potential or oxidation peak potential, this potential. And opposite side, where the reducing, this is the you can see this is the peak potential, this is the reduction peak potential, right. So, this is the reduction peak potential. So, okay, let us plot it clearly. I will show you much easier. Let us remove how to calculate the formal potential. So, we definitely need the formal potential before collecting our impedance data. So, this is your cyclic voltammetry, right. So, this potential will be your oxidation peak potential, and this potential will be your reduction peak potential, right. So, this is E of P, oxidation in anodic, right, anodic peak potential, this one potential of cathodic peak potential. Then the formal potential will be EP of the that is oxidation. We can mention this one PA, so this one will be PC. So, EPA plus EPC divided by 2. This is the E half or formal potential. So, this potential mainly we will apply for the impedance spectroscopy. So, why? In this potential, iron 2 and iron 3 will be in the reversible stage. So, they can easily form iron 2 to iron 3, iron 3 to iron 2. So, one electron we can this electron transfer will measure through this electrode surface. So, how fast this electron transferring through the electrode surface. So, as I mentioned just before, if it is highly conductive, easily it can transfer. If it is not highly conductive, it will not transfer easily. So, impedance accordingly we can measure. See, one thing just you have to remember, biological molecules they are not conductive much, right, like protein molecules. So, if your protein stops, they are immobilizing slowly step by step on the surface. So, slowly your sensor surface impedance will be increased, because they will hindrance the electron transfer rate for this conversations, right. So, that you have to keep in mind. While we will measure the impedance, we will measure the number of the proteins, how they are immobilizing on the sensor surface. Suppose you have two sensor surface, one is just antibody coated, another surface is antibody and antigen coated. Then definitely this two second electrode, this second this is first electrode, this is second electrode. So, this second electrode, it has the many protein stuff. So, its impedance value will be much higher than this. So, this impedance value will be much higher than the first one. Okay. So, much higher. So, let us show you one fundamental basic diagram of the impedance spectroscopy, how it looks like. So, it looks like this. One impedance spectroscopy, there will be the one semicircular region and with the straight line. So, in the electrochemical impedance, so I am not going very deep derivations, why it will come the semicircle, why it is a straight line. I just will explain you how we will use this one for electrochemical biosensor. So, in this impedance case, in the y-axis we will measure the impedance of imaginary and x-axis will measure the impedance of real. Why it's come the impedance of imaginary and real? Because you know in this impedance equation, mathematical equations, if we see, there is in the y-axis there is a I value, that is the imaginary value. Because of this we are getting the imaginary impedance, and x-axis we are getting the real value. So, that mathematical calculation I am not coming, just I will show you the practical application how you will use this one. Here I put the reference for this electrochemical impedance. So, if you want to understand the mathematical derivations, you can see this reference. Let us come to the biosensor applications only in this talk. See, so we will get one semicircle kind of region, one is a straight line. So, this semicircle region, so if you put like this way, so this region mainly your impedance. So, we are calling this one RCT, that is called resistance RC for charge transfer. So, this is called charge transfer resistance, or we say RCT. So, in the next few slides I always will say that RCT value will increase, RCT value will decrease. So, this RCT is nothing, this is the semicircle region. So, this is the, you can say, full radius we will measure from this semicircle, then we will see how much value we are getting. This corresponds to your impedance value. So, you can see here it started actually from not the origin 0, it started from something from here. So, why? Because solution itself has some resistance. So, this value is called the solution resistance or RS. That will not much give the importance, because solution resistance we thought that it will always same the almost the constant during the biosensor formation, it will not much change or it will not give much information. Which part will give you more information? That is the RCT value. This part will give more information. RCT is the charge transfer resistance, how electron will transfer through your electrode surface. And there is another part, the straight line, right? This straight line is directly equivalent to your mass transfer control. Mass transfer means when we are using the potassium ferrocyanide ferricyanide mixture, this mass how fast is transferring to the electrodes, that we will measure. See, one thing, when resistance will increase, this mass transfers also slowly will decrease, because impedance is increasing. No, so the mass transfers definitely it will be like proportional. When impedance increase, this mass transfer will be definitely decrease. Suppose you have the electrode surface, if you have lots of stuff deposited on the surface, then electron transfer rate through this will be decrease, and then mass transfer also from the bulk solutions towards the surface also decrease. That is why what kind of shape you will expect during the biosensor formation step by step, right. So, I can explain in the next slide also with giving a real example. So, first let us try to understand this image. So, this semicircle region, that is mainly the RCT value you will measure, this will give you lots of kinetic information, and the straight line, that will mainly give you the mass transfer control information. Kinetic means how fast the electron transferring towards the electrode, that kinetic information we will get. See, if your this semicircle region is increased, and definitely your this mass transfer region will decrease. So, you will get the lower, this line will decrease slowly when this will increase, then again increase means this slowly this straight line will be decrease, because mass transfer will decrease. So, this is the main informations for this electrochemical impedance. If you see the image of the electrochemical impedance, it will looks like this, and we can interpret like this way. Let's come to the real example, right? So we will develop a biosensor for suppose a bacteria cell detection. How the impedance spectra will look like, how we can predict. Okay, so you can see here, this one your transducer surface, and here first we will immobilize the antibody layer, primary antibody, that is very much specific towards the your target, that is the bacteria cell. See, before the bacteria cell there is lots of gap, and this transfer will be pretty fast. So you will see this kind of a very good electrochemical impedance diagram at the very beginning. So it will never start from the 0, because you have some solution resistance. So it will start something like this. So with the antibody, you will get like this. Now when you will drop the bacterial cell on the electrode surface, definitely the impedance value will increase. So what will happen? Then you will get something like this. See, this value will decrease, and this value, see, impedance value is increasing. So y axis we are saying Z imaginary, x axis is Z real. So this real value we will measure. So when we increase the this biological molecule on the surface, see, first RCT value this one, second RCT value is this one. Clear? Now if we increase target concentration, and slowly this value will be like this way, slowly we will see the change. Clear? So this is pretty easier method, means definitely from this curve we can predict that yes, some molecules actually immobilizing on the surface, and we are getting lots and lots target molecule on the surface, and based on this RCT value, definitely we can predict the number of the bacterial cell present on your sensor surface, and quantitative value you can predict, and this is very sensitive method. So if some molecules come, then more molecules come, definitely surface will be blocked by this cell, and electron transfer rate will decrease. That's why this method is very sensitive. Let's come another example. So in this example you can see how we can use the impedance spectroscopy. This is a very real example. Suppose you have one surface. I already showed you very first class that we can use some screen printed electrode. This is screen printed electrode. This screen printed electrode now let's use for the impedance spectroscopy measurement. So this one iron Fe to Fe3 conversion. So at the very beginning, the electron transfer rate will be very fast, right? Then we immobilize. See, because of the protein layer is forming on the surface, and kind of this this conversion from Fe2 to Fe3 will decrease, right? And because it is kind of hindering the electron transfer process. See, now we are slowly immobilizing one by one step. See, first we immobilize the antibody, then we immobilize some BSA. See, second step BSA. So why are we immobilizing BSA? I think I taught you at the few class before that you need BSA to decrease the non-specific binding. If you add BSA, they actually block the other surface where actually your target protein can bind. So it can, although I mean you have antibody, but they are not binding with antibody, but they are binding with bare surface area. So it will give you the wrong information. So false information you may get. So that's why that is empty side, it should be blocked. How we can block? By some small protein BSA, bovine serum albumin. So by this we can block. So definitely it is also protein. It also can little bit also it will hinder the electron transfer rate. So accordingly you also will get a electron transfer rate will decrease, right? So you will see the another change of impedance spectroscopy. Now you add your E. coli bacteria in the third step. See, so third step you are adding the bacteria. So definitely see it again blocking the sensor surface. So electron transfer rate again will decrease. Now see suppose you are not getting much difference on the impedance change, because there is some gap maybe and electron can transfer. So, what you will do, you can add the secondary antibody with this. So, secondary antibody also can bind. We are not using any label, just secondary antibody to increase the protein stuff on the surface. So, it can block the surface effectively. So, definitely it can hinder the electron transfer rate much more effectively than this third step. So, fourth step will be much more effective, right. So, we will get the accordingly the big change of the impedance spectroscopy, and we can predict the how many now actually bacteria present on the sensor surface. Let us show you the example here. If you measure the cyclic voltammetry, you can easily correlate the cyclic voltammetry change with the impedance spectroscopy. See, as I told, they are blocking the sensor surface. So, your impedance increase. So, suppose you are measuring in potassium ferroferricyanide mixture, you are measuring cyclic voltammetry first. So, suppose you are measuring the first step, number 1. Number 1 is just the bare surface. So, potassium ferroferricyanide can easily transfer the suppose first bare electrode, then second is the antibody, third antibody BSA, fourth is antibody, then the target. So, this is your 4 electrode surface. 1, 2, 3, 4. See, so first cases there is no protein, so electron can transfer easily. So, that is why you will get very good shape of cyclic voltammetry of potassium ferroferricyanide. Okay, and very good shape means the electron your electron transfer process is very fast, you will get the very high current, and E half value, your E half value also will be very low, and if you measure like E peak potential of anodic and peak potential of cathodic, this difference will be very low, because the electron transfer is actually transferring very fast. If electron transferring very fast, so this difference also will be very low. This kinetics maybe I will teach you again after some classes, but just try to understand the basic fundamental theory here, that when the electron transfer can happen very fast, then this value will be low and current value definitely will be very high. Now, you immobilize here the antibody, definitely protein stuff came, that is why electron transfer rate will decrease and current also will decrease, and slowly this gap means EP and EPC gap will increase also. So, second cases you may get like this, you may get like this. So, see, its EPA value also shifted towards right, EPC value also shifted towards left, and current also decreased. See, it means your electron transfer rate of the surface actually decreased. So, this impedance value should increase, right. You can see now the left hand side this impedance data. See, first the black one is the bare. If you see the bare one, as I told, because of the electron transfer is very fast, see the impedance value very low. That is why we are getting this small RCT value, right. So, this is the RCT. So, RCT is very low. Now, see antibody coated, this one. So, as you increase the protein stop on the sensor surface, see the electron transfer definitely will decrease. That is why see the RCT value is rapidly, this is RCT value increase, that is why. And your CV value accordingly you can see the difference, current value will decrease and your peak potential, anodic peak potential will be shifted towards the right and cathodic peak potential will be shifted towards the left. Clear? This first try to understand how your sensor surface will behave, and accordingly how your cyclic voltammogram will change and your impedance value also will change, and there will be very good correlation between the cyclic voltammogram and EIS. See, if the cyclic voltammogram see very good means very high current and this EPA EPC gap low, see the very low RCT, and then it is shifted towards the right, current decrease and your RCT increase. Now, let us come this step, third step. So, antibody and then we add some BSA. So BSA we add, definitely it is small protein, but still your impedance will increase. That's why you can see after BSA, if you see the cyclic voltammeter, see the current again decrease. See this one, current again decrease and little bit shifted, because this is not much decreasing, but still decrease. So you will see, that's why the change of cyclic voltammetry like this, and accordingly you will see the change of impedance, but not very much, very high, but you can see the change in CV and EIS. But you will see the vast change slowly if we increase the target concentrations, like if we increase the number of the E. coli concentration, then slowly you will see this cyclic voltammogram change, and also you will see the impedance change. It will be proportional to your concentrations of your target. Okay, I will show you now the another example. What's example here? You can see, just you have a bare gold surface, gold PCB. Now, as you know that if you have a antibody that thiol conjugated SH, then we can easily bind on the gold surface. So PCB means printed circuit board. So on gold printed circuit board, we are using a thiol conjugated antibody. Then we will get a, see, like this, thiol conjugated gold surface. Now we add the BSA. Now we are using the bacteria, and that bacteria is conjugating here on the surface. This is just another example. So I am telling that this is a very generic concept. You can use for any kind of applications for biosensor development, like for before case, like I show some E. coli detections. Here I am showing for S mutant detection, but concept is similar. Even you can go for the like SARS-CoV-2 detections, like other virus detections also. Like this common concept you can use for biosensor development, and accordingly you can see the impedance change. Okay, I will show you the very good image of the impedance spectroscopy. You can see this is a printed circuit board, just I told you in the last slide, like this PCB printed circuit board that is gold coated. We can use, and we can use some potentiostat where we can measure the impedance spectroscopy, and we can connect with the computer, and just see this area, we are in this area actually we are fabricating the working electrode. I mean, in the working electrode we are fabricating the antibody, then we are adding our target. Then accordingly we can see the impedance change on your computer screen. See, because your potentiostat, this is very portable potentiostat we are using. That's why this kind of technique also can be useful for point of care, for field testing. We can see the monitoring. We don't need much washing step. Just you can add the target concentration, and you can see the change on your sensor surface easily. So sometimes you may ask if you want to use the secondary antibody something, then how we can use this one? Do we need the washing step? And if we need washing step, is it useful for a point of care? That kind of all the questions I can address you after some classes, that we can use some microfluidic based sensor. Just we can add some extra buffer solution, and excess thing can be washed out. You can measure the impedance. The best things for measurement of the impedance is this. You don't need any very very important washing steps, and easily you can apply this technique, and it can be useful. That's why for point of care diagnosis. But that's why I am showing this image. This simple chip where we are fabricating our biosensor without washings also we can use. We can see this impedance value by using simple potentiostat. So that's why it is very much useful for on-site diagnosis also. Okay, in the next class I will teach you more and more impedance spectroscopy based, some level 3 based and some multiplex based sensor. You can see there is lots of other biomarkers we can detect at the same time by using impedance spectroscopy. Everything I will cover in the next class. Okay, so that's all for this class, and thank you very much.